Hi there, I'm Brendan Caulfield. I have just done a talk called Where Are We? Our Place in Space. And it starts off with a bit of Irish, but please stick around and enjoy.
I wanted to add a new thing to the channel.
Networking. It's basically all about the people.
My name is Borna Zuber. Welcome to my YouTube channel if you haven't subscribed yet.
As an intro to the interviews that I'm going to start doing in October, so that's one of the bigger plans that I have. Listen to something motivating. I think it will help a lot.
Díobh corcha, tá fáilte mór romh agus gan buchas libh as a teacht anseo. Anocht, testíonn im sibh a hart Turas ag tosnú durg anseo agus ag dul beagnach chomh fada gur féidir. I dro gur féidir file as bhaile chun ceist a thithe maigad. Bhfuil méid. Tá a féile orm nach bhfuil mé in an turas seo a dhéanamh as céilge. As barla a bheith mé ag labhart. Ach gam buchas ó chrí le bríd agus an cuiste deis seo a tabhairt dom agus fáilte chóireáil a chrúil sorry a thug siad dom. Tá mhór cabhar íon anois. Tar an éanacht lom an doras chun a náit I spás a amsú. Our place in space. Thanks everyone. Thanks everybody for coming. Good evening, you're all very welcome. Tonight I want to bring you on a journey starting right here and going almost as far as it is possible to go. All just to come back home and answer the question of the night, where are we? I regret I won't be able to do it in Irish, but I thank Breach and the committee for the welcome and the opportunity. And I'll need your help with this, so please come with me on this journey as we find out our place in space. So the title of the talk is Where Are We? And that's the first thing I'll need your help with. Where are we? Anybody tell me where we are? Geographically, where are we? Ballyferriter. So we are right here. So where is that? Give us more context.
Europe.
Europe. Here we are. Europe. Let's keep going. Very nice. So 53 degrees north on what? There's a Earth. The Earth. There's a clue there. So the Earth is part of, there's the moon, our solar system. If I turn on orbits, you can see there the orbits of the inner planets, and then as we come further out,
Which is Earth's orbit?
Earth's orbit is this one, the third. There's the orbit of the moon.
Is that going the right direction?
I hope so. As we go further out, we see the orbits of the outer planets. The inner planets fade into insignificance compared to them. Everything in space gains scale the further you go. As we pull out, the sun is another star. We see our neighboring stars here. If I turn on the labels, we see some names on them. Sirius, Procyon, Altair. So we pull back further, past the local stars, the ones that are bright in our sky, the ones that our ancestors named, we get to code names like HIP 32724 over there, or even longer coded names. That's just because, as you can see, there are too many to count. So we pull out further. This is the next line of our cosmic address, the Milky Way galaxy. That's a collection of about 200 million stars. We're not quite sure because it's hard to count them. We have some neighbors, Magellanic Clouds there, other little galaxies that orbit around us, and then nearby the Andromeda Galaxy there. Those two will collide in about 4.5 billion years, combining into 1 billion star galaxy. But even that fades into insignificance. We are always presented by larger and larger scales as we pull out into the vastness of the cosmic web. You can see waves of dots here. These dots, each one of them is a galaxy. Every streak that's going past is hundreds of billions of stars. This is the real scale of the universe. This is where we are.
How much of that is estimated or artistic representation?
It would be wrong to call any of this artistic. It's based on real data. It is statistically extrapolated. It is a representation of what is really out there, but we don't have the tools to measure all of this yet. Our tools are getting better and better all the time. But
So would that be based on, was it a probability then?
yeah, this particular piece of software models the probability of where a galaxy will be, how many stars that'll contain, and so on and so forth. It's not going to be predictive. You won't find a real galaxy in this real location unless, as many of the galaxies closer to home are, it's based on real data. But it's representative of the density and diversity that you'll find out there. And to illustrate that, I'll ask for another piece of help. Can I have a volunteer to navigate, please? I need someone to set our course. Come on, don't be shy. All right, point, hi there. What's your name?
You already know.
I already know your name. It's my nephew, Ivan. Not a plant, I didn't ask him to do this. So, point at any dot on that screen and we'll go see what's there. Okay. Good choice. Now, we are traveling at hundreds of billions of kilometers a second at the moment, so forgive me if I overshoot. So, what have we got here? This is a disk galaxy, central bulge. It's not unlike our own, in fact. Looks a bit thinner. I'll bring up the data for it now. So, I don't know what that galaxy type actually means, but it can tell us how many stars it is.
More blue.
Yeah, it's a bit fewer arms. There's only 2 major arms there. Ours is lower. There are hundreds of billions of, or hundreds of millions of blue suns in this galaxy. It looks young. The reason it's bluer, I'll just turn off those labels. The reason it's bluer is because it's younger. Younger stars tend to burn bluer. And so we're probably not going to find much life in this galaxy because those stars haven't been around for long enough to form life. Does anybody else want to navigate? Pick a star and go see what's there. Sorry, so as stars age, probably should go back to what stars are. They're conglomerations of gas that has fallen together after just drifting around in space and getting caught up in each other. As the gas gets denser, it has more gravitational pull, it pulls in more gas, and as all that gas collapses in itself, that undergoes a lot of heating, and eventually the pressure and heat inside it causes fusion to occur, which is basically burning, and that's what causes a star to form. So the presence of that mass there attracts more mass, and you get burning after a while. Depending on how much gas there is in the neighborhood when the star forms, it'll come out of various different sizes. So our sun is a relatively small star compared to many other stars out there. It's about average given the whole population, but there are much, much bigger stars. But early in a star's life, it's going to be burning hot and bright because it's burning the easiest elements to burn, it's giving off the most energy. As they get older, they get less energetic, give off more or less energy, so they burn at a lower temperature. And so you see that fade from blue or white hot down to yellow like our sun, down to red like Betelgeuse, for example, is a star that's been in the news lately. And eventually they'll either burn out into embers called white dwarfs or explode spectacularly, but we'll come back to that. So, who wants to navigate? Come on, someone not related to me. You, sir, you look eager. I'll hold still. You choose a star, we'll go see what's there. Just go and point up one there. That one up there. Okay. So this one, yeah? Okay. Right. Once again, we might overshoot her. Let's see now. Yep, sorry. As we come in close now, I'll circle around so we get a darker background. As we come in close, just pay attention to the glow. You'll see little sparks come out of it. That's just because we're getting closer and there are, well, okay, that kind of spoils it. There are objects that reflect the light from that star, and those will be planets. So let's see what we've got. Almost all stars in the night sky have at least some planets. This is something we didn't know until recently. In the last 20, 30 years, we've started to discover planets around other stars. Before that, our telescopes just weren't good enough. I mean, we couldn't see these dots of light until we were right on top of this star. Can you imagine trying to spot them through binoculars? So what we have here is a giant planet with moons. This would be a gas giant. I'm just judging that based on appearance, so I'll target it and see what info we've got. Because I have never been here before. I didn't set up this location. It's all entirely generated on the fly based on those statistical models. So we've got a hot sub-Jupiter. That means it's smaller than Jupiter, the largest planet in our solar system. It's hotter, so it's probably closer to its star. And these little moons, let's see what we've got. Where's my mouse gone? Yep, misplaced my mouse. Oh well, we'll judge it by eye. So this looks like a rocky moon. Hot, airless subterra. So this is a moon with a composition not unlike Earth, but it doesn't have the atmosphere that we have that gives life. Come down to the surface, we can get an idea of what it would be like to actually stand on this moon. Oops, that's under the surface of the moon. So, this is what it looks like on midday on an alien planet in another galaxy. Far, far away, indeed.
Is he given a number for gravity there, no?
Yes, gravity.
It says on the second bottom.
0.277.
Thank you. Yeah. So right now we're under the force of 1G. We just set that number because that's what it's like where we're used to it here on Earth. This moon would have just over a quarter of the downward pull that we're all feeling right now. You could jump 10 feet in the air on this moon. And the days and nights would be quite different as well. If I increase the time scale here, you can see the planet that it's orbiting doesn't move on the horizon. That's because the great gravity of that has slowed down the rotation of this moon until it's no longer turning. Oop, not sure what happened there. Much like the same thing has happened with our moon. That's why we always see only the one face of it. You can see the other moons in the sky circling around. You can imagine if this were a planet or a moon that would support life, people would be obsessed with the motions of those moons. They try to use them to predict the weather, to predict good harvests, to predict the outcomes of war. There would be arguments between the people on this side of the planet who could see the gas giant. Oh, I'm stuck in a mountain, sorry. Trying to illustrate something here, get out of the way. People who could see the gas giant on this side of the planet, moon, versus people over here on the far side who never get to see it. They'd think the people on the near side were mad talking about the great ball in the sky. Let's see what else is in this solar system. Thanks. Sorry, what was your name? I didn't catch it. Anthony?
Yeah.
Nice one, Anthony. Thank you very much. You can see that planet has no shortage of moons. That was what all those spots were that just vanished into the distance. Rocks and worlds orbiting a giant planet. Other worlds in this solar system. There's a twin planet set there. It looks like one of them is very, very warm. They're quite close to the sun. They're 382 degrees Celsius. And the age, 1 billion years. Earth is 4.5 billion years old. It took about 1 billion years for life to emerge on Earth. This star, as I said earlier, like most of the stars in this blue galaxy, is young and bright and energetic. And there hasn't been enough time here, probably, for life to emerge. So there's no life in this solar system. Now, we haven't found life outside of our own solar system, but we have a fairly good guess on what the requirements for life are. There's enough unknowns for us to not be sure if life exists anywhere else at all. There's a lot of reasons to think that it does, there's a lot of reasons to think that it does not. But if it does, it may be unbelievably far away from us, or it may be quite close.
Why was Beetlejuice in the news?
Good question. So heading back home, almost home, to Beetlejuice, or Betelgeuse, however you want to pronounce that. This, sorry? It is, and there's an interesting reason for that. This is a star that we could see in the night sky outside if it wasn't raining. It's about, how far away, Killian? There you go. It's a red giant. It's in the final phase of its life, and the reason it's warped is because, and you can see it's quite orange, reddish color. It's running through the last of its fuel, and the fusion at the heart of it, which is a fusion explosion, essentially sustained. That's what the sun is. It's a continuous explosion caused by the incredible pressures and temperatures at the center, pushing outwards against gravity. Gravity and the outward force of the explosion in our sun are perfectly balanced, so that's why it's so completely spherical. This star, as you can see, is a bit lumpy. You can get up closer to it and see that more so. See the bumpiness there. It's actually, this program is simulating a very unfortunate planet here, very, very close to the star. But, yeah, see you guys. Anyway, it's lumpy because the fusion reaction at the heart of it is running out of fuel, and it's uneven. So you're getting surges and pulses of fusion erupting out of the star, and then gravity is pushing that material back down when the surges subside. And this star, in reality it is a real star, is in the constellation Orion. It's usually the 11th brightest star in the night sky, but in the last few months it has dimmed by more than 30%. It's now the 21st brightest star in the sky, no longer the brightest star in its constellation. And the reason for that dimming, it is suspected, is that it is getting into the final stages of its death. It's going to, sorry? It's going to blow up. It's going to run out of fuel. The fusion explosion at the center will stop. Gravity will win that fight. The entire mass of that star, which, by the way, our orbit around the sun would fit into about that center of the star. So the entire mass of that enormous, unimaginably huge star is going to collapse in on itself, and all of that stuff is going to smack into the center of the star and bounce back out in the most titanic explosion in the universe, called a supernova.
Sorry, Brendan, you said in the last few months it dipped by what percent?
30%.
So this is happening rapidly.
Yeah, it's been happening rapidly. Now this star, because it's in this stage of life, it does tend to vary in brightness. There's a predictable cycle of boom and bust, essentially, in the fusion reaction at the core. And it runs at about every 180 days, it gets 5 to 6% brighter and then dims back down again. And every 5 to 6 years, there's a similar cycle, about 10% variability. So there's a few different cycles that are happening there, but in the entire time that the scientific community has been observing this star, it has never dimmed to the degree that it has dimmed in the past few months.
Was this is 650 years ago this happened, is it?
Yeah, so we're seeing, not in this representation, but when we look at it with our eyes in the night sky, we're seeing it as it was 650 years ago, because the light from that star takes 650 years to get here. So we're seeing it in its past state.
So that's what, like 14th century or something?
Yeah.
So could it have already exploded now? We don't know yet.
It could have, yeah. And that may have already happened and the light is just on its way to us. We haven't got the message yet. When it does arrive, we'll certainly notice, because the brightness of that explosion, even, and just to give you an idea of what a light year is, 1 light year is 10 trillion kilometers. So what is that? 6,500 trillion kilometers light will take 600 years to traverse. Anyway, when it does blow, it will outshine the full moon. It will be visible during the daylight. You'll be able to read books by the glow of this explosion.
And how important a star is it to us?
It's not really an important star to us in the sense of like existential issues. The explosion of the star won't cause any damage to Earth, but mythologically, sorry? Probably not. No, I mean it is part of a noted constellation, but it's not something that we vitally depend on for navigation. If I go back to Earth and look back at it.
So we get fragments of Earth when it explodes?
Well, light is the fastest thing in the universe. Nothing can travel faster than light.
Could we potentially get fragments from the Earth?
Potentially, but what I'm getting to is that because light is the fastest possible speed that anything can go at, everything else is going slower than light. And it'll take much, much longer than 650 years for any fragments to potentially get here. However, that's a really good question, because that's the source of new stars and new planets. A star goes supernova, it explodes its guts out into the universe. And when a star is fusing matter, when it's burning, it's not just getting rid of that stuff that it's made of. It's taking elements like hydrogen and helium, really simple stuff, and fusing it into more complex stuff like carbon and iron and lead and molybdenum. The entire periodic table of elements is composed of stuff kicked out of stars when they blew up, with the exception of hydrogen and helium, the very basic stuff. Sorry, there was a question?
Gold.
Gold, yeah. Gold. Yeah. All of the gold that we have, all of your jewellery, every scrap of gold that has been accessed or is accessible to humanity on the Earth was dropped there after the formation of the Earth by asteroids that were flinging around in the formation of the solar system. All the gold that came together when the Earth was formed was heavy, so it sank to the center of the liquid molten lava planet and is in a layer around the core, pretty much inaccessible to humanity forever. But gold, lead, all of the heavy elements, those are formed in the last few seconds of a star's life. So Betelgeuse will collapse in on itself, and it'll run through the fusion of gold and lead and name the heavy elements. I can't, not very good at the periodic table. But it will form all of those in those few seconds and then spew them out into the universe in clouds of gas and dust. And those clouds of gas and dust will float around for millions, tens of millions, hundreds of millions of years until something disturbs them. It may be a passing star, it might be another supernova going off, it might be another cloud of gas colliding with it. Something will cause the uniformity and sparseness of that cloud to condense a little bit. And then we're back to that situation earlier on where a dense knot in the cloud causes a gravitational pull. You've got more gravity coming from this dense knot in the cloud, that pulls in the neighboring bits of the cloud, that pulls in more, you get that collapse happening again, and a new star is born. So I think the Sun that we orbit is a third or fourth generation star. So there's been 3 or 4 generations of stars that lived out their lives. They had planets, they had all sorts of, wake up, all sorts of stories and adventures and potentially maybe life occurring around them. They got to the end of their fuel, they exploded, putting out all of this enriched material from their cores, and then those clouds of gas and dust came together, gravity ran its course and pulled the star together. So,
what's the difference in the, you've been talking about the formation of stars being suns, yeah?
Yes.
So a planet forming, what's the difference?
It's a very similar process. So around, I was actually going to try and find one for you there. Around a star that is forming, it's pulling in gas and dust and stuff from its local neighborhood, and should have a circumstellar disk here somewhere. Okay, I can't find one, but this, yeah, this will be similar enough anyway. Around that forming star, you get gas, dust swirling around. It's conglomerating, coming together in the same way as the star did originally, but it's a more energetic environment, so it gets to clump up a little bit, and then you get gravel, and then that gets disturbed, and then those bits of gravel maybe come together into little asteroids, and that gets disturbed again, and you get asteroids coming together. Over the course of tens of millions or hundreds of millions of years, this cloud of gas and dust surrounding a star, which looks very much like this, starts to condense into larger and larger chunks, and those larger and larger chunks can pull in other large chunks. They come together, they form planet-like clumps. There are generally lots of collisions that will occur inside that disk, lots of breaking apart and sort of planetary cancellations, and eventually, as everything gets hoovered up by the heavy stuff, the heavy things pulling in all of the loose bits, you'll get planets forming. They get to settle down, they get to form their molten lava crust from all of the pressure and heat of their formation, and you start to see a recognizable solar system like we have today. That's how the Earth formed. That's how we are here. All of the matter of which you are made, if you look at your hand and think about the molecules and atoms that make it up, they're made of elements, and those elements were cooked in the heart of a star and then exploded into space. And that's why we're here now. Betelgeuse, when it goes, may undergo a more extreme process even than that at the end of its life.
When supermassive stars collapse and that smack together occurs, you can have a phenomenon happen where the universe just says, no more. There's so much matter falling in, which is collecting so much mass into such a small space. It causes the pull of gravity to get more intense than reality can really deal with. It pulls open a hole in the universe, and the universe just says, I'm done.
I can't deal with this. And that mass exits the universe, essentially. You get a black hole. That's caused by the pull of gravity being so strong that not even light, not even the thing that can transmit information can escape. And this is what a black hole looks like. So I was using this as an example of a forming solar system. It's actually kind of the opposite, but they look similar enough. This black thing in the center, surrounded by this arc of light, is the ghost of a star. And the reason the light is arcing around it like that is because the gravity is bending light around what used to be a star. That blackness inside is all that's left.
Could you say then that that's basically what's happening there is you're distorting the coordinate system?
Yeah, it's essentially the same idea. If you work it out mathematically using the coordinate system and following the laws of general relativity, that's what you'll come out with. You'll come out with coordinates that stop making sense in the traditional way. It's bending the space around it rather than things traveling through the space and going into it. It's a monster.
Just one more question, sorry, Brendan.
Yeah.
It's just someone over there asked earlier about like will we get hit by anything? If
Mhm.
light is, we'll say, the first contact we make, like it's the fastest, we can say it's like the shock wave.
Yeah.
Would there be a second wave then, maybe some kind of plasma that could come a month after it, that's just behind?
Yeah, there are
So
some.
we get hit with that like a month after we see the thing flare in the sky.
Yeah, there are subatomic particles that can get up to very close to the speed of light, so you would get kind of echoes in those in those kind of energies, but the reason they can get so fast is because they are extremely insubstantial. They have almost no mass, so the wave of neutrinos is I think the term for them. The wave of neutrinos that would wash over the Earth would actually barely interact with the Earth. So it might flood this room and wouldn't affect any of us. It would pass through at nearly the speed of light, we wouldn't notice it. It might not even hit a single atom on its way through the entire planet. That's how insubstantial that particular wave of energy would be.
Would we be able to detect it?
Yeah, there are detectors. So when I say it might not hit a single atom, it's 1 in 10 million that it would. So if you fill a room with something that will react energetically to a collision with one of those items, and you have 10 million, say, liters of water, which is what they use, you'll potentially detect one collision. And the way that they do that is they have extremely sensitive photoreceptors, basically cameras lining huge underground caves. There's one in Japan, which essentially just has a lake in it, and the entire wall is lined with these cameras, and it just sits there in complete darkness waiting for a flash of light, and that flash of light will tell them that, oh, we've detected a neutrino, and that probably come from an exploding star much further away than Betelgeuse, potentially millions of years ago.
So if that cave lights up, we're done.
No, it's of almost no consequence. It's scientifically interesting, but there's no harm that can come to us from a neutrino burst. It doesn't interact enough with normal matter to bother us. And the rest of the product of a supernova at a distance like 650 light years, first off, it won't bother us for thousands upon thousands of years, and by the time any of it gets to our neighborhood, it'll be like a gentle breeze. It's so dispersed. The main impact will be to our night sky for a number of weeks. Extremely bright light in the sky. So, speaking of black holes, you may have heard of a recent news story. It was, I think, last year or the year before. And I might end on this.
So the way that you're saying that planets light up,
Yeah.
and the Will that not bring heat then as well as the material? They're not like fry a section of the Earth.
You would have to, you'd have to have a neutrino beam of such insane energy and so highly focused to even boil an egg, that you would need to supernova like 1,000 stars at once and have their polar jets aimed directly at Earth. It would need to be an incredibly unlikely occurrence.
The Betelgeuse can't change the temperature of the Earth like in these worlds.
Not in any kind of measurable way, no. But there are some stars, and I mentioned a polar jet there. You may have seen on that, there's an illustration of one there. Stars get them too when they, you see these lines going off here? That is where the magnetic field around the black hole has been twisted around in itself so much that it's almost like the barrel of a gun. And all of the stuff that's falling into the black hole that doesn't get, you know, the right angle to actually fall into the black hole, gets deflected sideways, gets bent around into that magnetic gun and shot off the poles of it. The same thing happens in a collapsing star, because the stars are chock full of really complicated twisted magnetic fields that are insanely powerful. So anything in the star, like iron atoms or anything that has a tendency to obey magnets, you know, something that would stick to the fridge, will get pulled along with that. And as that star collapses and all of those get squished down together, they give a burst of incredible energies off the poles of the star where those gun barrels are. So in theory there is a danger from nearby supernovas if the star's poles, that is the axis around which it rotates, happen to be pointed at Earth. And that could be dangerous. So it would give a burst of extremely energetic light, gamma rays, X-rays, lots of really nasty stuff at extremely high energies. And you could maybe fry one half the planet, the half the planet that's facing that star at the time that it goes nova. But again, that's incredibly unlikely. The star would need to be very close by. There are no stars of that type close by. The only one that could even potentially have that kind of impact on Earth, we know that the poles aren't facing towards Earth, so there isn't a danger from that.
So when we hear of a solar flare,
Yeah.
and it knocks out communications or satellites and that,
Yeah.
that's a form of radiation, is it, as opposed to what we're talking about?
So there are a couple of things that come out of a solar flare. First is, radiation. You get a shower of, I think it's gamma rays come off solar flares, and that's the initial thing, and that can be dangerous for astronauts in very high orbits of the Earth, beyond much of the protection of the magnetic fields, because those gamma rays, X-rays, can cause cancers. So astronauts generally have a higher risk of cancer, but only to the degree of like someone who's had maybe 100 X-rays in their lives. So it's a slightly elevated risk of cancer. That gets higher the further you go from the magnetic field of the Earth. So people on a trip to Mars would have maybe the risk of cancer of someone who smoked 20 a day, for example. But that's cancer in later life. It's not that they're going to get cancer right then and die immediately. It's just an elevated risk. With a solar flare, you get that burst of radiation. That's got some risks associated with it, not too terrible. And then after that comes the actual material that was burped out by the sun. And that material will be these kinds of charged particles. In fact, the reason the flare went off was because of these magnetic fields that are so twisted up inside the sun. As the sun is roiling with its heat and energy and convection currents and everything, all of those magnetic fields are getting tied around each other, and sometimes they will snap, and that snapping kicks out a load of material because it's all magnetically influenced anyway. That's what a solar flare is. So when that material bursts out, it takes significantly longer, of course, than the light, the radiation takes to get here. The radiation travels at the speed of light. It is a form of light. It takes maybe 8 minutes to get here. The burst of material will take several, sometimes hours if it's really, really strongly kicked out, but usually days to get to Earth. We have satellites in orbit of the sun that will give us warning of this. And when it arrives, it's carrying the electric charge that it had when it was inside the sun. And as that material interacts with Earth's magnetic field, it gets pulled down towards the atmosphere in various kind of shells that come in at various latitudes around the Earth. And that will cause charging on the surface of satellites, so you might get satellites burning out or computers resetting on the satellites. And if it's a very, very powerful solar flare, that can cause charging on power lines on the surface of the Earth. In 1812, I think it was, if you Google the Carrington event, this was a solar flare that went off, and at that time, of course, we didn't have much electrical infrastructure, but we did have Morse code communications. And Morse code operators were electrocuted in their chairs because the charged particles charged up the lines and sent electricity through their bodies as they touched their Morse codes out of their Marconi sense. There were other people who were a little more careful and were able to observe that you could still send messages even when you disconnected the power source, because there was so much charge in the lines that the set worked. If that happened today, that level of electrical charging in our infrastructure would fry microchips. It would absolutely disable the internet, cars, planes, all kinds of infrastructure. That is a serious threat, but it's not a world-ending threat, it's just a society-damaging threat. It's something that could happen in a month. It's something that happens quite often in terms of flares of that power. It's just that rarely is Earth in the firing line for that. There have been a couple of close calls. We got the edge of one, I think, last year, but wasn't direct enough to actually hit us and cause an event like that. But yeah, so I was going to bring us back to black holes for a moment. And as I said, I might end on this. Oh, I didn't even look at nebulas. Okay, one brief aside.
Where did the Romulans attack Mars?
It wasn't the Romulans, it was synthetics. So, after a supernova, just to rewind a little bit, those clouds of gas and dust that get kicked out tend to look really, really pretty. That's the only reason I'm showing you this. This is what it might look like after Betelgeuse supernovas, several million years after.
Will Betelgeuse, when it goes pop, is it likely to take out the planets around it?
Yeah, very probably. In fact, remember when I was at it and there was that planet just barely skimming it? That guy's toast. Betelgeuse is now a lot bigger than it used to be, because as it gets older and sort of weaker against gravity, it puffs up. And it's constantly puffing off outer layers. If you remember, there were waves of material around it. So that planet was probably one of the mid to outer planets in that solar system in its early days, but the star has since expanded and eaten the inner planets. And our sun will do something similar when it gets old. Now, it's not big enough to explode in a supernova, but it will puff up and will probably get pretty close to consuming the Earth. But that's 5 billion years out, so I wouldn't be too worried. But this is the kind of thing that would be left after a supernova. Big old space brain. Anyway. So this is another black hole here. But this one is one that you might have seen before. I meant to have a picture ready to go, but I don't. You may have seen the... You may have seen the image that was all over the place last year. This fella. That was an image that was taken by, I think it was 22 different telescopes all around the world, combining their power through a process called interferometry. And it's this guy here. It's in a different wavelength of light, which is why it looks a bit different. If I lower the exposure, it might start to look a little more similar. But yeah, this is a black hole at the center of galaxy M87. And that is, it was 55 million light years away, something like that. But it's a monster. It's rather than that being the ghost of one star, that is the ghost of tens of millions of stars. Because just like in the formation of a star, the formation of a solar system, the formation of a planet, stuff in space floating around out there, zero gravity, it has its own gravitational pull. Things tend to come together, they tend to stick together. Black holes are no different. That black hole at the center of that galaxy was once millions of stars that all died, became black holes. Those black holes started to mingle with each other and came together to form this. We have been detecting gravitational waves, another thing you might have heard in the news. That's the signature of black holes bumping into one another, essentially. They spiral around each other until they combine, and while they're spiraling, they're sending out ripples in the fabric of reality, the space-time, ripples of gravity. When they combine, they'll stop. So you get to hear this sound, which I should have also prepared to play for you. But it goes whoop, which is the sound of the ripples in space-time increasing in frequency until they just stop. And that's because the two holes merge into one giant hole and there's nothing to cause ripples anymore. And that happened countless times to create that black hole. There's also one of those at the center of our galaxy. It's the mass of 40 million of our sun. So I don't have a way to cap this off, to finish off, so I guess I'll just say thank you very much for the talk. I hope that has illustrated for you where we are. Hope I didn't get too sidetracked because I could just keep going forever. Does anybody have any questions?
Fascinating.
Oh, you're welcome.
Yeah. It's only the tip of the iceberg, really, isn't
Can
it?
I ask you an odd question?
Absolutely.
I don't even know if I can formulate the question really.
Far away.
Alright, so you got Danny Healy-Rae, have you heard the guy?
I've heard of him.
Saying that, you know, in 18-something, the wettest 10 months ever.
Okay.
If Trump doesn't believe in climate change, if you take, we've had an ice age, they didn't have coal burning power stations then. The amount that the world has changed in hundreds of years, 200 years, 400 years.
Yep.
Is climate change really having to do with the whole of the process of actually the sun possibly getting a bit weaker? Things changing in the space rather than actually we burnt a lot of coal.
The climate has changed in the past in response to changes in our star's output. There's no question about that. Climate change as a phenomenon has historically, had a lot to do with the output of the sun, various other astronomical influences. But what we're seeing now is unique in that a lot of people point back to, can't remember the name of the particular die-off, but there was a carbon dioxide event in the historical record where a huge number of species died off. It's one of these great extinctions, like the one that killed the dinosaurs. But in this case, it was because the atmosphere became very carbon dioxide rich quite quickly. Now, in that case, that quite quickly was over the course of 40,000 years or so. We've seen the same change in carbon dioxide over the course of 40 years in this last century. So it's pretty stark that it's nothing natural that's causing this change. But yes, to answer your question, absolutely the climate is affected, of course, by changes in our sun.
I'm sure I'm standing on an ice crater or a berg standing here about probably 2 kilometers deep.
Yeah. And indeed, if there wasn't the level of carbon dioxide in the atmosphere that there has been for the last 50,000 years, we would still be in the midst of an ice age, because carbon dioxide is a temperature regulator, but it's extremely sensitive to change. The atmosphere in general, extremely sensitive to change. So you change that by a few tenths of a percent, and that regulated temperature starts to go off the boil, or on the boil in this case. And it tends to run away with itself. So there's, yeah, there's
What keeps the carbon dioxide not just going
into space.
Yeah.
In part, it's the Earth's magnetic field. In part, it's because carbon dioxide is, compared to the other gases in the atmosphere, not a lot heavier, but it's around the same weight. So it mixes well with the gases in the atmosphere. It doesn't float to the top like hydrogen would, for example. Hydrogen and helium, they're very light gases. So every time you pop a balloon, you're actually wasting some of the Earth's precious supply of helium. Because that will just float to the top of the atmosphere and get blown off into space. Yeah, so the magnetic field stops that solar wind, the output from those solar flares, from stripping the atmosphere off the Earth. That and the mixture of the gases as well. Okay.
Just one last question, sorry, Brendan. Resonance.
Resonance.
Is there any sort of resonance really, effect, was it practical effect of resonance between stars?
Between stars, I'm sure there probably is, but there's a great example of resonance actually between planets in our solar system. So I'm just heading back home now. What distance was that? Okay, yeah, 50 million light years, yeah. Sorry, I'll just speed that up. So, there's our sun. How are you? Zoom out a bit. Just a few tens of millions of miles. Kilometers, sorry. I'll just switch to some more illustrative camera mode. Right, so these are the orbits of the planets. And if I speed up time a lot, you start to see that sort of beautiful clockwork motion. If you pay attention to counting off, say, that inner one there, which is Jupiter, and the outer one at the other end of my finger is Saturn. So it's 1, 2, 1. There's a resonance there, I think. 1, 2, 2, 1, 2. So like, yeah, okay, it's slightly off, but there are resonances in the orbits of the planets.
This is what between
So the
Jupiter and...
yeah, so sorry, this ring here is Jupiter. This ring here is Saturn.
Yeah. You mean when they pass each other?
Yeah.
Right there.
So there's definitely on the inner planets, I know that there's some fairly clear resonances. So this is Mercury, Venus, Earth.
Is that what planetary alignments are then?
Yeah, it's when they're kind of passing each other, and it's why things are so predictable, because there is a degree of resonance.
When you say resonance, what do you mean?
So resonance is like, I can't remember what the relationship is, but it's something like 3 orbits of Mercury to 1 orbit of Venus, and then 2 orbits of Venus to 1 orbit of Earth, and then it's almost 2 orbits, or it's just over 2 orbits of Earth to 1 orbit of Mars. So the reason those are occurring is just that the gravitational pulls of the planets as they orbit the Earth are actually speeding each other up and slowing each other down at various times in their orbits, and they'll find a sort of a niche where those relationships remain stable. Just because if they're not in those niches, they get pulled either away from those niches or towards those niches over time. And that's what resonance is. It's a sort of a stable, repeating pattern of influences between 2 or more bodies. And that's what you're seeing here. So it's essentially about counting how many times it goes around versus the next one going around. And so there'll be a 2 orbits to 1 orbit kind of relationship, or 3 orbits to 1 orbit, 2.5 orbits to 1 orbit. It varies, and I wish I had a more precise answer, but yeah, resonance occurs in solar systems.
What is the software
This is called Space Engine.
Okay.
It's available for free on spaceengine.org. There's a paid version on the gaming service Steam, which has slightly better features. The free version is pretty much full featured. It just lacks a few of the latest features. It's made by a single developer, a Russian guy named Vladimir. He's been working on this for, I think, 15 years. And he's been releasing it all the way, and I've been following it for about 10 years. Yeah, I just think it's fantastic. It really, really brings home the sense of scale of the whole universe.
What do you call it again?
Space Engine.
Brendan's underselling himself there because he's contributing, aren't you?
Well, I gave him a few pointers and ideas here and there, but I wouldn't say I'm a contributor as such. Stuff like the way that the light is bent around the black hole, I had some say in how that was done, but Vladimir covered.
That was brilliant.
Sorry?
That was brilliant, like, because I've seen pictures of black holes many, many times, but it's only now that they're kind of starting to make any kind of sense, like, you know?
Yeah, it's, if we're talking about the software side of things, it's really customizable as well. So if I go back there, okay, well, the point is you can change various parameters. I was going to try and make this black hole look a bit more like the one from Interstellar just by messing with the temperature of the gas around it and the thickness and visibility.
Or you can warp the black hole, right?
Yeah, you can change, like you could fly to any planet, open up the editor and play with the settings on that planet, because it's all based on the various statistical properties of the planet that it just kind of, not randomly, but sort of intelligently generates. It's given a set of mathematical rules for what planets would be where around a star, what the composition of the surface of them would be, what their atmospheres would be like, and various interrelationships between those factors. And so that's how it generates all of this richness. But you can play with all of those variables. So if I could bring it up, I'm not sure why it's not coming up for me, but
is Vladimir going to change this? Is he going to amend this software to reflect what's happening with Betelgeuse now?
oh yeah. He's continually updating it. In fact, this black hole, I don't know that was in the software before the news story about it being imaged last year. There may have been a stand-in for it, but it's a hell of a lot more accurate now. Stuff like the interstellar objects that was detected in 2017. Yeah, I was going to try and pronounce it in the Hawaiian way, or something like that. But that was added in as well. It's quite weird.
Is it in there?
Yeah, it is. I'll look at it.
And what's peculiar about that again? It's speeding up as it comes through.
So yeah, well, many things are peculiar about it, not least that it looks a bit funny. It's so generally speaking, astronomers will be looking for new objects like comets and asteroids in the sky. They'll look at one photograph of the night sky, look at the next one, switch back and forth. They'll see a dot that moves and they'll go, oh, I've discovered a comet or an asteroid. That's great. Let's map the orbit of it by extrapolating from that movement what its path around the sun is. When they discovered this guy, they extrapolated the path and it didn't close. It didn't form an ellipse or a circle around the sun. It formed a U shape. And what that was telling them was that it came from somewhere else, fell into the solar system, and then the sun bent its course around the sun and accelerated it back out of the solar system. So it's a visitor. It's just dropping by. If I turn on its orbit, you should be able to see that. So I'll zoom out. The other weird thing about it was when they were determining its shape by how the brightness changed as it tumbled, they found that it's very narrow and very long, which is very strange in itself. And then as they watched it approach the sun, as you mentioned, Ciann, its course seemed to change. So you can see the U shape there. It's coming in from outside the solar system. This must be a while back actually, because it's already on its way out now in reality. But you can see how it gets close to the sun, and then the sun's gravity changes its course and sends it back out this way. The strange thing though was that it was acting as if it was under thrust, or as if it had some kind of gas is being expelled from it, which would be normal for a comet. As a comet gets closer to the sun, anything that's on it that can boil will boil, that gas gets expelled out, and just like a rocket engine or a thruster, that gas leaving the surface has an effect on the course of the comet. It's very, very minor, but it does affect the course, and that's detectable. So people will see that happening with comets, and it'll help them determine properties of it, like what kind of gases are on it, how much there is, and so on and so forth. But the thing is that you can see that gas. You can see it as a coma or a tail from a comet. Think of Halley's Comet in the night sky and the beautiful tail behind it. But this didn't have any tail. It didn't have any visible emissions coming from it, and yet it was changing course ever so slightly. So they have never really nailed down what it was, but they're sort of assuming it was gas that for some reason couldn't be seen. But this yoke came and went. It's still in the neighborhood, but it's on its way out. This must have been, the date must be set to last year or the year before.
It's 2017.
Is it? Okay, that makes sense. If I set it to now, yeah, there you go. So it's on the way out. So it's not yet past the orbit of Neptune, or I'm going to pronounce it as Uranus. Which is supposedly the correct way to say it. But yeah, it's on its way out.
And
very mysterious object. Yeah.
I presume they plotted the trajectory back to see where it could have come from.
Yeah. There's nothing significant on its backwards trajectory, but because of the speed it was traveling at, it has been millions of years since it encountered another star. And over that time, all of the stars are orbiting the center of the galaxy anyway. They're all perturbing each other's orbits as they pass by one another. So as you go further back in time, it gets harder and harder to determine what star was where when. Because it's an incredibly complex thing to calculate, with all of the interactions between every other star, because all stars are pulling on each other. And as they get closer, they pull on each other more. If two stars pass by, you see the same kind of changing course as happened here. Since that visitor, there was another one detected, and it made this one just look weirder, because the most recent one that was detected was just a bog standard comet. It emitted gas, it looked just like it should, it moved just like it should, it was round, it was unremarkable. It was just like a comet from our solar system, but the trajectory indicated it came from elsewhere. So that makes this one kind of weird, especially when you look at it up close, and it looks charitably like
but they didn't get
a Frank Lloyd Wright sculpture. Sorry, yeah.
I heard they didn't they basically want a better term. That's an artist's impression. They didn't
Correct.
actually get a
Yeah, so there was nowhere near this level of detail obtained on it. So all that's known about this thing is that it was approximately 4 to 8 times longer than it is wide. That it was tumbling end over end, which I think we'll see.
4 to 8.
Yeah. So it's long and thin, which is super strange for an interstellar or for any kind of object in space. So of course there are people saying, well, that sounds unnatural. Is it a spaceship? There was another measurement that was done on it which kind of supported that as well, which was that the way it was, so as I said, they weren't seeing any gas coming off it, and the way it was being pulled by the sun's gravity, the fact that they weren't seeing gas coming off it, maybe there's very little gas coming off it, but for that little gas to have this much effect on the course of the object has to have very low mass. So then people were saying, well, is it hollow? And as you get more and more questions like that, it starts to form like the idea of a hollow, long object sounds like a ship. So
with the way that it's spinning like that, is that accurate the way it's tumbled?
Yeah.
Like that?
Yeah. So that was
that kind of general, like, you know, it's like what's the thing like you know, with balancing systems,
gyroscopes.
Like a gyrodyne or something. Yeah.
Yeah. I mean, things in space tend to tumble. You get influences that affect one end of it more than the other. That would be that the light from the sun, or gas that it's passing through, or whatever it bumped off a million years ago, and it'll still have that spin. The Earth is a prime example. It spins once every 24 hours. That's inherited from the disk that it formed out of. So the fact that it's spinning isn't necessarily a clue to anything, really. But yeah, it's a strange object. Unfortunately, at the moment we don't have any kind of spacecraft that could chase it. So it's lost to us. It came, it confused us, and it left. But now, like these days, we're getting really, really good at spotting these kinds of things. We're getting really, really good at spotting asteroids and things. So that's really good news as well, because it used to be rare that we would spot an asteroid that would be on an Earth crossing trajectory. Now we're catching a lot more of them, and we're catching smaller and smaller ones. So that'll give us a lot of warning if one is on its way to give us a bad day. And it also means that we're going to catch more of these interstellar visitors. We expect that most of them will be unremarkable, like the most recent one. But if there's anything like this again, we'll soon have the capability to actually go out and check it out, which will be fascinating. Can you imagine? Like, yeah, especially a human mission to one of these objects. Somebody setting foot or you know, zero-G grabbing onto an object that formed around another star. That's amazing to me. Entirely foreign. Yeah, that'd be amazing.
Thank you.
Yeah, you're very interesting. Thank you very much. What an image then, though, huh?
Hi everyone, my name is Borna Zuber, and today I have Brendan Caulfield here with me. Thank you very much for joining us, Brendan.
You're welcome.
Tell us, you did the brilliant talk last Friday on space and where we are. Can you tell us a little bit more about that?
Sure. So I'm Brendan. Thanks very much for having me. We work together here, and you very kindly agreed to help me out with that, which is brilliant, and your support has been invaluable.
Sure.
So what are we talking about? I did a talk with a sort of town committee in Ballyferriter, which is a town on the Dingle Peninsula, close to where Star Wars was filmed. And it's kind of a long story, but I got involved with them because they got a telescope for sort of a photo shoot as a prop for Star Wars Celebration Day, and I kind of got pulled into that whole mix of astronomy and that because of my interest in space. I've been interested in space for, well, my whole life really, through science fiction, and then about 10 years ago that sort of morphed out of the fictional realm and into reality. And so I've always been wanting to share this excitement of the cosmos, I suppose you'd say, with people in general. So when they asked me to do a talk, I leapt at the chance, and yeah, I got into it using software to sort of visualize what I was talking about.
The software was Space Engine, right?
That's correct, yeah.
It looked really good because it represented like everything from a small scale, like a planet, to like a galaxy. It looked really cool. And what are the sort of topics that you discussed in the talk?
Yeah, so utilizing that capability, I wanted to communicate the most mind-blowing thing to me, which was the most mind-blowing thing about this kind of field of knowledge is the sense of our location. So you sort of, people sort of go around, I think anyway, I did before I learned all this, that you've got like your address, you know, I'm here in Tralee in Ireland, in Europe, and maybe you think about the world, but everything outside of that is kind of
that's kind of it. Yeah.
But when you zoom back and zoom out with a knowledge of the universe, you get so much more context, and you also get along with that the history of where you came from, what you're made of, where that originated, what's going to happen in the future as well, and it's all super cool and interesting.
But you went also into a lot of stuff that's a bit out there, you know, like chemistry and physics and things that people don't consider actually related to space, because they're thinking like, oh, it's just like planets out there. But you discussed processes really well and how everything is connected there. So
well, like I said to Breach, the organizer, I have approximate knowledge of many things, and so I was able to sort of touch on a lot of those things without having full detail on it. But it's all related because the title of the talk, of course, is "Where Are We? Our Place in Space?" and that question sort of encompasses it all. Chemistry, physics, all of these processes that occur, they occur in the universe, and we live in the universe. We're in space right now.
Yeah.
That fact alone kind of eludes a lot of people, and I think it's kind of an exciting one to point out. Have you ever been to space? Yes.
Yeah, sure, all the time.
Yeah, exactly. So, yeah, all of that I sort of don't view as unrelated. It's all something that follows on from the central topic.
Cool. And as far as I saw from everyone's reactions, they loved the talk. Could we expect more talks from you like that, and will it be like a regular thing now?
I think so, and I hope so, yes. It was the first time I'd done anything like that. I'd never really done public speaking before, aside from one disastrous incident in secondary school, but no, I'd never done it before. I was a bit nervous going into it, but I was quite happy with how it came out, and the feedback I've gotten has been really good. And you have videoed it for me, thank you. So that'll be uploaded on Borna's channel.
You'll see it there, guys.
Yeah, soon enough. Yeah. And yeah, thanks again for taking me on.
No problem. Well, as far as I see it, it went well. I think people loved it, and there were a lot of questions at the end. Were you kind of preparing for questions, or were you just kind of like hoping that it would go kind of towards where we were aiming at?
Yeah, I had it in my head that there'd probably be questions coming out of it, because like I just tend to kind of do this on a one-on-one basis anyway. People, you know, I mentioned I'm going out with my telescope, or I mentioned that I'm working with the software, and people ask me questions about what it entails, and then that develops into longer and longer answers. So given that I was giving out a lot of sort of top-level information on a lot of topics during the talk, I thought, yeah, there's going to be a lot of follow-up here. So I had planned for a few questions. I got more than I expected, which is great. But yeah, essentially, yes, I did plan for questions.
All right.
And it, yeah, came out good.
Yeah, well, I'm glad that you're satisfied with the talk. I personally loved it, and guys, I hope you will love the talk. We'll put it up in the YouTube for you to see it now. So yeah, stick around, because Brendan's gonna do more talks about space, and join us in the journey to finding out where we really are. And guys, before you go to the next video, definitely subscribe to my YouTube channel, share it with your friends, and leave me a comment so I know how you liked it. Like my Facebook page, Power Balls, where I sell protein balls. On Instagram, I show really cool pictures from the day. On Twitter, I follow some influencers and information on tech. I also use Snapchat for short videos, but most of the time I spend on LinkedIn, where I put out more serious content because of my job. I also use TikTok to make viral and cool videos. I don't have a blog yet, but I'm working on my Steemit platform, which is a blockchain platform. Guys, thank you again for watching. I'll see you in the next video.